Hey everyone, welcome to today's Explainer. We're jumping right in today to unpack a piece of everyday magic that, well, you've probably seen it right in your very own kitchen. Think about the last time you were getting ready to cook. Maybe you were heating up a skillet for some pancakes or a wok for a stir-fry. To test if the pan was hot enough, you know the trick. You flipped a few drops of water onto the surface.
And when you did that, you probably noticed something kind of counterintuitive. If the pan is just warm, the water simply sizzles and boils away into nothingness, right? But if the pan is absolutely scorching, like literally glowing red hot, the water behaves completely differently. Instead of instantly vanishing, the droplets skitter, dart, and dance around the surface like tiny hyperactive glass beads. So why does that happen? Why does extreme heat seem to make the water survive longer, instead of just instantly destroying it?
Okay, Section 1, the dancing droplet mystery. Let's dive right into this.
Notice how perfectly spherical these droplets are as they hover above the glowing red pan. They aren't flattening out or spreading across the metal at all. They're maintaining their shape, looking almost like solid glass marbles suspended in midair. There is a very specific physical reaction happening here, allowing them to literally levitate right in the face of extreme heat. So this everyday magic actually has a formal name, the Leidenfrost effect. Whenever water dances on a ridiculously hot surface instead of boiling away on contact, you are witnessing this effect in action. It perfectly explains our kitchen magic. But to really grasp what's going on, we need to look a little closer. Moving right along to Section 2, Anatomy of the Effect. To understand how the droplet survives, we've got to isolate the specific physical components at play here, because it's not just about water and heat. No, it's about the highly structured environment created in those crucial fleeting milliseconds of contact between the liquid and the metal. Now, what's really interesting about this slide is how distinctly the layers separate. You've got the water droplet sitting right up on top, the intensely hot surface down below, and wedged exactly between them is a microscopic layer of steam. Now, because gas is a relatively poor conductor of heat compared to solid metal, this tiny cushion of vapor acts as a literal physical shield. It insulates the rest of the droplet and prevents it from instantly boiling away.
All right, Section 3, the four-step mechanism. Let's break down exactly how this happens.
This whole thing unfolds through a highly predictable chain of cause and effect. Step 1. You need a surface significantly hotter than the boiling point of water. Step 2. Rapid vaporization occurs the very microsecond the water approaches the metal. Step 3. That vaporization creates the protective vapor layer. And finally, Step 4. Elevated and protected, the droplet effortlessly glides and moves.
So, the crucial point is really centered on Steps 2 and 3. The surface is so intensely hot that the very bottom of the water droplet evaporates the instant it gets close. Actually, before it even truly settles on the metal. This rapid, instantaneous vaporization is what gives birth to that protective shield. Basically, the droplet sacrifices its bottom layer to create a steam barrier that protects the rest of the water. It is just a stunning display of self-preservation through physics.
And that brings us to the visual payoff, the dancing. Step 4 happens because the water droplet is essentially resting on a cushion of gas, rather than solid, grippy metal. This nearly eliminates all the physical friction between the water and the pan. The droplet is literally riding its own microscopic hovercraft of steam, which is exactly why the slightest tilt of the pan, or even a tiny current of air, causes it to effortlessly glide, dart, and dance across the surface.
Okay, final part, Section 4, Discovery and Real-World Physics. The name of this phenomenon comes directly from the guy who discovered it, a German medical doctor and theologian named Johann Gottlob Leidenfrost. Now, he didn't have high-speed cameras or modern thermodynamic sensors back then, but he was a really keen observer of the natural world, and he carefully documented exactly how water behaved when introduced to extreme heat. And, remarkably, he made this discovery in the year 1756. I mean, just think about that for a second. Over 2.5 centuries ago, scientists were already captivated by this exact same physical reaction. It's a huge testament to how long humanity has been studying the intricate laws of heat and matter, way before the modern era of physics even started. But listen, this isn't just some ancient trivia fact or a neat little kitchen trick. It is foundational science. The Leidenfrost effect is absolutely critical for major academic exams, including the NEET and the JEE. And it's a staple of Class 11 physics curriculums. Why? Because mastering this effect means you understand the fundamental rules of phase changes, heat transfer, and thermal conductivity. These are the very principles essential for engineering and real-world physics. And this brilliantly illustrates how a simple, everyday kitchen observation scales up directly into rigorous, complex thermodynamic equations. It gives us the framework to understand how the physical world operates, from a simple frying pan all the way up to advanced high-tech engineering. Which leaves us with a really fascinating thread to pull on. If a microscopic vapor layer can so effectively protect a fragile drop of water from the scorching surface of a red-hot iron pan, well, where else in our modern high-tech world might we harness this exact same effect to survive extreme, unimaginable heat? Definitely something to think about the next time you see a droplet dance in your kitchen. Thanks for joining me on today's Explainer, and keep questioning the world around you.